Hi everyone, welcome to GemChem. Now today's video is on chemical kinetics part 1 video, and here we are going to deal with extent of reaction, stoichiometric number, rate law, rate of reaction, order and molecularity. Now this is a topic in the BSc second year syllabus and we are going to deal with it in details. Now before starting, if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. And you can connect to GemChem more through the Facebook page, Telegram channel and Quora space. Now let us start. Now chemical kinetics deals with rate and mechanism of chemical processes, right? And it decides how rate depends on different parameters like temperature, pressure, presence of a catalyst or inhibitor, and we will see each of them in details. Now first topic of discussion is extent or advancement of a reaction. Suppose if we consider a homogeneous solution having a reaction which is also homogeneous in nature. That is, we are seeing a general homogeneous reaction. So this is our reaction, and as we know that nu1, nu2, nu3 and nu4 are the stoichiometric coefficients of the ith species in the balanced stoichiometric representation, and these are always whole number. They cannot be reduced. Now if we try to take these two reactants towards this side, then they will be deducted from it. They will be subtracted from the right hand side entity, right? So here that thing is being done. So ultimately we get that 0 equals to summation of stoichiometric coefficient and A1, that is species summation, their product and their summation. Now if you want to write it like this, that is this equals to 0, then you are completely wrong. These two are never equivalent and this must be understood very carefully. Now this nu I is the stoichiometric coefficient of the ith species in the balanced stoichiometric representation. This is unitless and independent of time. It is negative for the reacting species, as we have seen here. It turns to be negative, and positive for the product species. Now what is extent or advancement of reaction is very important to understand regarding this. Okay, it is represented by this symbol. This, while writing, we write like this. Okay, xi, and this extent of reaction is actually a proportionality constant. The change in the number of moles of species during a reaction is directly proportional to its stoichiometric coefficient. Now the stoichiometric coefficient is nu I, right? Where proportionality constant is the extent of reaction, and we will see in the next slide that how it is represented, right? Now say this one, delta Ni is actually our difference in the number of moles. Okay, so delta Ni is proportional to the nu I. Delta Ni can be written as equal to extent of reaction, that is epsilon nu I, and if we break it out, then Ni1 equals to Ni0 plus nu I epsilon. Now this one is the number of moles of the ith species at time t. This is number of moles of ith species at time 0, and this is a function of temperature and have a unit of mole. So this will be highly clear when we complete the sum present here. So see, in the reaction given here, suppose that the initially 0.8 mole of ammonia, 0.7 mole of hydrogen and 0.2 mole of nitrogen is present. At a later time t, the mole of hydrogen is 0.55, which is present. So we have to find out the extent of reaction and also find the moles of ammonia and nitrogen at time t. So let us see. Now first we need to write down the reaction carefully. So 2NH3 gives N2 plus 3H2, right? So at time t equal to 0, it is Ni0, which is 0.8 here moles, here it is 0.4, and here it is 0.7. Now when it is time equals to T, then Ni equals, we don't know for ammonia, we don't know for nitrogen, but we know for hydrogen, right? Now we will see the next step. We know a single formula, that is Ni equals to Ni, 0 plus nu I extent of reaction. Now for this particular case, we know both, that is Ni and Ni0, right? So we will just substitute the value. So here it will be 0.55 equals to 0.7 plus 3 epsilon. Now from here we can get the value of epsilon to be minus 0.05 mole. As I have told you, the unit of epsilon is mole. Now if we want to find out the number of moles of ammonia, then it will be like this. Ni equals 0.8 given plus 0.1. That is, we multiply 3 into 0.05. Ultimately here we get 0.9 mole, and moles of nitrogen, if we try to calculate, then here nitrogen is 1, so we will multiply 1 into the extent of reaction, right? And in this case we have multiplied with 2 because there was 2 ammonia. So Ni equals to 0.4 plus minus 0.05 equals 0.35 mole, and this is our answer. So this is how we do the reaction, and we can find out the extent of reaction, number of moles of different reactant and product. Now we will see what is stoichiometric number. This is another important part of the basic of chemical kinetics. So see, actually stoichiometric number is the number of times a given step in a mechanism occurs for overall reaction, is the stoichiometric number or numbers of the step. So if you see this example here, 2N2O5 gives 4NO2 plus oxygen. So here mechanism shows that this particular step occurs 2 times, the next one occurs 1 time, and the next one occurs 1 time. So here the stoichiometric number for this step is 2, for this is 1, and for the last one it is also 1. So this is the answer, and here this is the only method of finding stoichiometric number, and from stoichiometric number we can understand that a step can occur twice or thrice or once. So first reaction step will occur and should occur twice, and the other 2 steps 1 time each. Now remember, as we have seen the value of this one, that is extent of reaction, is always 0 when time is 0. Now whenever time is increasing, this extent of reaction will also increase, and this is directly proportional. So this is an important point to be remembered about, right? Now we will see the next part, that is rate of reaction. We have already seen in class 12 that we have directly used the equation to get the rate of reaction. But how does it come? What is the initial basis of that? We have to see from here, right? Now rate is defined as a conversion rate per unit volume of the reactant system. It is intensive in nature. Now what is intensive, what is extensive is already discussed in chemical thermodynamics video. If you have not watched it, I will give the link in the description box as well as the I button present above this video. You can watch it. Now this particular rate of reaction depends on the pressure, temperature, presence of catalyst or inhibitor, concentration. Now this rate as I have told you is a conversion rate per unit volume. So this is 1 by V, and differentiation with respect to time of extent of reaction. This is the conversion rate. Now if somebody asks that we know that rate is intensive, but what about this quantity, that is d by dt, is it extensive or intensive? Since this is a conversion rate, this is extensive. Remember this can come. This is extensive quantity. Now we are going to derive the rate of reaction from this particular equation. Now see, here we know that Ni equals to Ni0 plus nu I, we are using eta, 0 plus nu I d eta. So we can write d eta equals to 1 by nu I d Ni. So this one was our first equation and this is our second equation. Now we will put 2 in 1. Put 2 in 1, right? So now the rate becomes like this. Rate equals 1 by V, 1 by nu I d Ni by dt. We will assume what? We need to assume something. Assuming that volume of reacting system, which we will see, volume of reacting system is taken constant. Volume of reacting system is constant, or it changes by only negligible amount. So we are actually trying to ignore this volume term. Okay, so negligible amount. Now the rate becomes like this. That is, rate equals 1 by nu I, here d Ni by V, we are taking this V inside, by dt. So ultimately we get it like this. Ni by V is our concentration, we know that, right? From kinetic theory of gases, we have already dealt with it. So here ultimately the most resultant one, which we have seen all the time, that is, rate is given by 1 by nu I d concentration by dt is being obtained, and this is the rate expression. So this is how we can obtain the rate expression and use it in different reactions. Now we will deal with rate laws. So let us see. Now rate law at any time t is experimentally found to be proportional to various species concentration present at that instant of time raised to the power. So it is actually concentration raised to the power something. Okay. And rate law must be always determined experimentally. It cannot be obtained from seeing the reaction mechanism. So rate constant, if you see here, we need a rate constant. It is independent of concentration but dependent on temperature, and this is very important. Now see, rate law is an equation that expresses the rate of reaction as a function of concentration of all species present at same time. So in a reaction, the species present at same time is taken during an experiment. So this is actually function of concentrations. Now it cannot be deduced from reaction stoichiometry. As I have told you, in some cases it reflects the reaction stoichiometry, but it is actually coincidence and reflects the feature of underlying chemical reaction mechanism. It is a guide to reaction mechanism, and at different condition rate law changes, and this is a part of chemical kinetics. Now how can we know or monitor progress of reaction? There are different methods. We need to know few methods. We will discuss briefly as we do not have this in deep, right? So first method is chemical method and second is physical method. As you can see, this chemical method is tedious, whereas physical method is convenient and mostly used. Now see chemical methods. Chemical methods includes cooling the reaction mixture. Suppose we are under lab conditions and we are doing hydrolysis of ester. So we need to react alicate with acid by titration to make sure that no further reaction takes place, we need to cool it or dilute it and then study the reaction. So this is difficult. We have to take it to an extreme level to study the different progress of reactions, right? Another method is that diluting the reaction mixture, that is this one. Next is that we can add foreign species which will specifically, mask the one of the reactants, and then we can see the rate of reaction or progress of reaction without that reactant, right? So it removes one of the reactants. And the last one is that we can remove the catalyst and see the progress of reaction. These are different methods of monitoring a reaction using chemical methods. Now if we want to see the methods of physically, there are different methods. First is that we can monitor pressure versus time graph, provided at least one component is gas to monitor the pressure. Next comes our mass spectrometry, electrical conductivity, ionic conductivity, spectrophotometry. Now measurement of intensity of absorption at a part of the spectrum is done here. Absorption is directly proportional to the concentration, right? So more absorption, more concentration. Next, it can be detected by pH metry, NMR spectroscopy, electron spectroscopy, gas chromatography. So these are the different methods, right? Now we will see order and molecularity, and this is the last part. So this is very important part because from the next video we are going to deal with different orders of reaction, right? So what is order? What is molecularity? First of all, order is taken throughout the reactions from the rate law, from the rate equation. So if you see here the rate, that is here given equation. So these are individual partial orders, that is the powers are partial orders and the sum of the powers is overall order. What is molecularity? Molecularity of a reaction is the number of reacting species that take part in an elementary step. So if a reaction is occurring in one step, in single step, then the number of reacting species participating in that step is the molecularity. And order of an elementary step, suppose if we are considering order of one particular step, then order and molecularity are equal, otherwise they are different, right, for the whole reaction. So if we try to see that order of an elementary step is always equal to molecularity, so we will see one of the example, right? Now if we take, for example, for this reaction alpha A, this is the stoichiometric number, beta B is P. Now we are applying law of mass action, from which we can get the rate law. So from here we can write our rate as this one, that is rate is equals to K A alpha B beta, because they were present as stoichiometric number, right? So stoichiometric coefficient, more specifically these are actually stoichiometric coefficient, right? Now order, from here we can write alpha plus beta, and since the reaction is taking place in one step, so here molecularity will also be alpha plus beta. Why? Because here alpha number of A's are reacting with beta number of B's. So ultimately we can see from here that these two are equal, and this proves that order of an elementary step always equals to its molecularity, right? Now remember this alpha, beta, gamma, whatever we have seen here, these are the stoichiometric coefficients. These can be negative, positive, 0, integer and fraction, okay? And overall order, which we have seen here, overall order, this can never be negative but can be 0, okay, can be 0 at most, right? If we change condition, change reaction mechanism, then order also changes. This particular order does not depend upon stoichiometry, right? Now from the next video we will deal with different ordered reaction. Now next video specifically we will deal with zero order reaction and first order reaction. So stay tuned, and this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.